Okay, so we're taking a look at the RBF OLS algorithm, or orthogonal least squares. And so the way we're going to start is we're going to be starting with the design matrix. And so we can suppose that we're looking at our W hat times our phi hat. And the way this equation is going to run is the way we're going to think of this equation as starting is we're going to be thinking of using all the data as centers. And if we do that, you'll remember that what we're doing is interpolating the data. And so, yeah, this is overkill, right? And so, by the way, let's think about what the sizes of our matrices are. So what's the size of W hat? So that's going to be M by K plus 1, but K is actually P now, right? So that's going to be M by P plus 1. And then instead of having P centers, right, we have P data points. So this is actually P plus 1 by P. And then this would be M by P still. Okay, because that doesn't change. So what we're doing is this is kind of our initial, we're thinking of this as like our initial setup. And what we would like, our goal, somewhere down here at the end, is to find centers so that our new values of W hat is going to be M by K plus 1 times our new design matrix, which is going to be K plus 1 by P. And then that way we would like to be approximately equal to T, right? So what we're doing is we're trying to find rows of phi that we can use. Well, we could look at it either one of two ways, right? We could think of which rows of phi hat do I need to keep in order to get a good mapping. And then we'll toss the rest. Okay, now I should also mention that each row of phi hat, each row of phi hat corresponds to a data point, right? Because there are p rows of phi hat, each row corresponds to a data point. And so when I talk about which rows do I keep, so which rows, well, I need to move up a little bit, I guess. Or maybe I move over. Oh, maybe I'll move over instead. No, I can't get the thing to move. There we go. Okay, so anyway, in place of which rows do I keep, I'm going to substitute that with which data points are centers, right? Because if I say I want to keep rows, say 2, 10, 15, and 20, those are the four, then this corresponds to saying, this is exactly the same thing as saying use data points 2, 10, 15, and 20 as cluster centers, or centers for the RBF, I should say. Okay, and so this is orthogonal least squares. This is the setup. So let's review that again real fast. So you start by assuming that every data point is a center. We start by assuming that every data point is a center, and you go through the rows of phi hat to see which ones do we need to keep in order to get a good mapping. So there's some other questions I need to answer here. But my goal is to go from this equation to this equation, right? So I'm only keeping k data points, okay? And so the interpretation of that is that whatever rows I'm keeping, those correspond to the data points that I'm going to use as centers, okay? Of course, there might be an issue right off the bat. What happens if the optimal centers are not data points? Well, then this would not be a good algorithm for that. There's other issues as well, but actually this algorithm works very, very well for small data sets, and of course that's why MATLAB, it has been a mainstay in MATLAB's algorithms. Okay, so this is the goal, and how am I going to do this? So let's take a look at what we have here when we're starting off in terms of the rows. So I've got my matrix W, got my matrix W hat, and then I'm thinking of the rows as being long, right? And then this is my T. I'm running out of space for my T. Maybe I drew this too big. I'm trying to do this kind of visually for you, so it kind of makes sense. So I'm kind of thinking of the shapes like that, right? And so, by the way, don't get caught in the trap that what we're doing on this side. So normally, what we would do in this kind of a problem is we would say, well, if I take A times B, what is that? Well, this is a linear combination of the columns of A in B, right? And so I would think of this matrix as being set up as in terms of its columns, but I don't want to do that because the column space here, remember, is going to change because we started with these are going to be columns. Start with columns in RP plus 1 and then go to RK plus 1, right? And this, by the way, is going to always be columns are always in RM. So you don't want to get in the trap of looking at columns of these two matrices. This is the phi hat and T. Okay, but the rows are in the same space, right? Because they're P units long in both. Good. So therefore, that's why we're looking. So therefore, yes. So that's why we're considering the rows of phi hat and the rows of T. Good. All right. So now, how am I going to do this? I need to somehow look for or keep the rows of phi that keep a good mapping. How am I going to do that? Well, here's the idea. I've got the row space of phi hat and a row space of T over here, and they're probably not going to be the same. Because this is a well, at the most it's rank M, right? Well, the way I've drawn it, it's like an m-dimensional subset of RP, and this over here would be a k-dimensional subset of RP. That's not counting the B's, because our last row, by the way, is all ones. We just keep that. That's going to be kept automatically. So let me get to the point here. We want to look for the row in phi hat that best points in the same direction as a row in T. Good. And so that's the one we're going to keep. This would be the row to keep. Okay. That is the orthogonal least squares algorithm. There's some more to that, but boy, I must be really rambling on today. Uh, that's what happens when you get old. I'm going to be like Grandpa Simpson with an onion on my belt. Okay, we'll talk more in the next video. Hopefully I'll get the onion off my belt. Okay.